Hello everyone, my topic is preliminary mechanical characterization of the small bowel for in vivo robotic mobility. I will introduce this topic in the following order: the purpose of the experiment, factors affecting robots in the small bowel, main methods of the experiment, and finally show the results of the experiments. First, the purpose of the experiment. Robotic endoscope is an advanced technology. It can complete tasks that cannot be done at present, such as gallstone removal, distal bowel biopsy acquisition, distal identification and repair of ulcers. However, the small bowel is a challenging environment for in vivo microrobots. A robot must navigate a tortuous path, often steering around 180 degrees bends, ascending and descending mucous membrane-covered surfaces, and traveling against peristaltic forces generated by the migrating motor complex. In addition, the bowel wall is soft, delicate, and narrow, which constrains the size of a robot, and provides minimal mechanical support. By studying the mechanical properties of the gastrointestinal tract, the robot can have better movement. The figure shows a kind of microrobot, which is about the size of €1. There are four main factors affecting robots in the small bowel. Active forces enact on an intraluminal robot, which creates by the motor activity of the small bowel, and the distal stomach. Biomechanics varies throughout its length of the small bowel. It varies along the circumferential as well as longitudinal directions. For in vivo mobility within the small bowel, a robot must overcome the adhesion of the opposing sides of the lumen in order to the passage. Studying the friction between the robot and the mucus is very important for the movement of the robots. The following devices were used in a single live porcine model. The figure shows the migrating motor complex force sensor in vivo. This device consists of a temperature sensor, manometer, and an array of custom natural latex rubber force sensor balloons that expand to the nominal inner diameter of the bowel. Before using the migrating motor complex force sensor, it needs to be calibrated. Sensor pressure and contact force are recorded. Verify that the force versus sensor pressure change is independent of the location and distribution of the load on the sensor. Two migrating motor complex force sensors are placed in the middle and distal regions of the small bowel to gather data simultaneously. After the two sensors are in place, the small bowel is placed back inside the peritoneal cavity. Record 15 minutes of blood pressure, body temperature, respiratory rate, heart rate and migrating motor complex force sensor data. Using the biaxial test apparatus to measure the mechanical response of the intestinal wall tissue to stress, 16 samples are tested in this part, secured to the biaxial test device, with nylon wire and 4 equidistant hooks on each sample side, and 4 black marks are placed in the center of the serous surface of the sample. The black markers form the corners of a 2 mm square, whose positions are tracked in real time, and are treated as nodes of a 4-sided finite element, which allows direct measurement of deformation from the material. The maximum tension level for the tests is set to 140 newtons per meter. Through the following formula calculation, the experimental results and the maximum shear angle can be obtained. The picture clearly shows the experimental device and process. Adhesivity values from this test are useful for a preliminary evaluation of energy needed for a robotic endoscope to overcome mucoadhesion. Force and position during separation are recorded, and calculate the total energy required to overcome adhesivity of the collapsed bowel by the formula. By using an in vivo tribometer to study tribological characterization, a live section of the small porcine bowel is pulled through a small incision in the abdominal wall. With the mesentery intact, the bowel is cut open along the longitudinal axis, and placed on the tribometer specimen tray. The force required to pull the sled divide the weight of the sled, to obtain the coefficient of friction. The graph shows the results of active force characterization. The left one is the mean radial contact forces per centimeter of the middle part. The other data is the sensor which places in the distal. The figure on the left shows 3 tissue samples, one each from the proximal, middle, and distal regions of the small bowel. The tissue exhibits behavior typical of collagenous material. The biomechanical response of the tissue is stable and repeatable after preconditioning. The picture on the right shows that the tissue behaves anisotropically, with the circumferential direction exhibiting more distensibility than the axial direction. The results are shown in the table, and the work required for separation at different positions is calculated. The energy required for the small bowel with a total length of 15 meters is about 0.55 joules. There is no significant difference in the coefficient of friction for proximal, middle, and distal regions of the small bowel. The figure shows the coefficient of friction versus sled position for 3 runs on a single sample taken from the distal small bowel. The coefficient of friction varies over the length of the test segment. The explanation is that the local changes in topography due to the many wrinkles and folds in the muscular mucosa affect the coefficient of friction. The creation of such a model will assist in the design and optimization of an in vivo micro-robot capable of intraluminal motion. Finally, thanks for your watching.